You've seen it everywhere, right? From ChatGPT to real-time translation, these AI language models are just part of our lives now. But what's actually going on under the hood? What's the blueprint that makes them all tick? Well, in this explainer, we are going to pop the hood on the engine that powers them all, the Transformer architecture.
So, what's really the engine behind this whole AI revolution? It all comes down to a single, pretty groundbreaking idea called the transformer. We're going to break down exactly what it is and how it powers the AI you're probably using every single day. Let's dive in. All right, here's our game plan. We'll start with the big picture, what a transformer even is. Then we'll get our hands dirty and look at the key parts of the engine. After that, we'll see how it actually processes language, how it learns, and finally, where this incredible technology is taking all of us.
Okay, so first things first, what exactly is a transformer? Well, in short, it's the architectural blueprint for pretty much all of today's most advanced language AI. It's the set of rules that lets a machine finally grasp context, nuance, and meaning in a way that feels almost human.
At its heart, a transformer is a special kind of neural network. Now, older models, they had to read a sentence word by word by word. But the real magic, the big breakthrough here, was that a transformer could look at the entire sentence all at once. This gives it a massive advantage in understanding the deep context and all the complex relationships between words, no matter how far apart they are in a sentence. And believe me, this was a total game changer. When Google researchers dropped this paper back in 2017, it pretty much made those older models that had to read word by word, well, it made them obsolete almost overnight. By processing words in parallel, all at the same time, transformers became way faster and so much more powerful, paving the way for all the big names we know today, like GPT-4.
All right, so if the transformer is our engine, what are the actual parts inside that make it run? Let's pull up the blueprints and break this machine down into its most important components.
Now, this list might look a little intimidating, but don't worry. We're really going to zero in on the three big revolutionary ideas here. How text gets turned into numbers, this thing called the encoder-decoder structure, and of course, the secret sauce known as the attention mechanism. These are the parts that really changed everything. Okay, so it all kicks off with a simple idea, turning words into numbers computers can understand. First, a process called tokenization chops up the text into smaller pieces. Then, embedding converts each of those little pieces into a long list of numbers, a vector. But here's the key. Since the model sees everything at once, we need one more crucial step, positional encoding, which basically adds a little tag that tells the model where each word was in the original sentence. Now, most transformers have two main parts, an encoder and a decoder. The best way to think about this is like a two-person translation team. The encoder is the expert reader. Its only job is to read the sentence you give it and build a super rich, contextual understanding of what it means. The decoder, on the other hand, is the expert writer. It takes that deep understanding from the encoder and uses it to generate the final output, word by word. And here it is, the absolute secret sauce, the attention mechanism. This is the breakthrough that makes transformers so ridiculously powerful. Think of it like a spotlight. For any single word it's looking at, the model can shine a spotlight across the rest of the sentence and figure out which other words are most important for understanding its meaning. That's how it knows instantly that the word bank in riverbank means something totally different from the bank in bank loan. It's all about context. Okay, so we've got the parts laid out on the table. Now, how do they all fit together and actually work? Let's follow a sentence as it moves down the assembly line from the moment you type it in to the final output. This right here, this is the heart of the whole operation. So after your sentence gets turned into numbers, it enters the encoder. And it's not just one encoder, it's actually a whole stack of them, where each layer builds a richer and richer understanding. Inside every single one, that self-attention mechanism is firing away, constantly figuring out how every word relates to every other word. Then the feed-forward network crunches all those connections to find even deeper patterns. Once the encoder stack has this complete, nuanced understanding, it hands it all over to the decoder, which then starts writing the output. But, a brand new engine doesn't know how to do anything, right? So how does it learn? The training process is absolutely massive, but we can basically think about it in two main phases. First, it goes to school, and then it gets specialized job training. So, phase one is called pre-training. Think of this as sending the model to college for a general education. It basically reads a huge chunk of the internet. We're talking books, articles, websites, and just learns the general patterns of language, grammar, facts about the world. Then comes fine-tuning, which is more like on-the-job training.
Here, the model is trained on a much smaller, specific data set, like maybe a bunch of customer service chats, to become an expert in that one particular task. And I really want you to understand the sheer scale of this college education. Training a big model from scratch is just an immense computational challenge. You're talking about months of time running on hundreds of the most powerful graphics cards available with an energy and hardware cost that can easily top $1 million.
All right, we've built the engine, we've trained it, so what can it actually do? Let's talk about where this technology shows up in our daily lives, and more importantly, where it's all going.
The applications are just everywhere now, right? From the obvious stuff like machine translation and summarizing long articles to generating all kinds of creative content. But here's the truly mind-blowing part. This whole architecture, this idea of attention, it's not just for language anymore. The same fundamental concept is now being used to analyze images, audio, even things like genetic code.
So, what's next? Where is all this heading? Well, the next big race is all about efficiency and scale. Researchers are desperately trying to make these models cheaper to run while also expanding their memory, or what's called their context window. The holy grail here is to build an AI that can read and understand an entire novel or a massive scientific report all in one go.
And of course, as these models get more and more powerful, new and serious challenges pop up. It's not just about making them smarter, but also about making them fair, ethical, and trustworthy. A huge area of research right now is called interpretability, which is basically trying to understand why a model makes the decisions it does. Peeking inside that black box is a massive technical hurdle, but it's absolutely crucial for building systems we can actually rely on.
This all leads us to the biggest question of all, doesn't it? As we build these models to be smarter, faster, and more efficient, how do we make absolutely sure that they're also fair and unbiased? Because remember, they learn from our data. So as they get powerful enough to process basically all of human knowledge in an instant, the great challenge ahead isn't just about what they can do, but about ensuring they reflect the best of who we want to be.